Hello and welcome again to this video about the weighted residual method. Now, this is a method that could sound familiar to you because the weighted residual method is discussed in many bachelor programs. But of course I understand that the details of the method may have faded a bit by now, so there will be a short recap given in this video, and in the next video we will apply it to the finite element formulation. But we're only going to discuss the Galerkin method in this video, which is one of the many weighted residual methods. So it's good to know that there are other methods that exist, but it's not necessary for you to be aware of all other techniques for this course. If you're interested, you can of course dive deeper into the different weighted residual methods, but for this course, the content of this video is more than sufficient. Before diving into the weighted residual method, I want to take a step back to the definition of equilibrium. Any physical system that's around you can be defined mathematically by means of a differential equation. As we discussed before, when you first studied about equilibrium, you may have done a simple example where there was on a flat surface an object which was bottom heavy, as shown here. When we applied a certain force to it, it would start to rotate or move like a pendulum. But in the end, it would come back to its equilibrium position, like it was at the start, called the equilibrium position. But there were also situations or structures where the system did not come back to its equilibrium. When you apply a force on this T-shaped part, for example, you would throw it over. It would fall on its side, which basically means that this now becomes the new equilibrium state. What has happened is that we have changed the physical state or the location of this problem. And all mathematical formulations of a problem like this are always looking for this equilibrium. And the only way we can find equilibrium for these cases is to find out what is the final state of rest or the final state of equilibrium. So now, if you get the idea behind this, you probably understand that it's very important to know the state of equilibrium for any structure. Now, in the same way, if we come back to the example that we've been dealing with so far, we see that there's a force applied P. And we know that because of this force, there will be a certain deformation under which this part will be in equilibrium. What is being done in the finite element method or when solving a differential equation is to find out this state of deformation that leads to equilibrium. So basically, we want to find out what this displacement is. So that's the principle of finding a residual. But how do we link this exactly to this residual? That will become clear in a few minutes. Because first I want to go back to the basics and to state again the differential equation of this problem, which is a as a function of x times e du dx minus p is equal to 0. Since we have a differential equation, we also have a boundary condition. And that is when x is equal to 0, u is also equal to 0. So now we have the boundary condition and the differential equation. So now the idea is that I have to find out the displacement u that satisfies the differential equation and the boundary condition. So now, rather than trying to solve it directly, which we've done so far, I will assume a certain displacement function where some constants are still to be determined. And next I put this approximate displacement function, u approx, in the differential equation. Since the approximate function will not satisfy the differential equation exactly, there's a residual that remains, and that's where the name of this method comes from. You can also look at the residual as some kind of an error, which is introduced by assuming this function. And our goal is to make this error or the residual go down to 0, or at least as small as possible. And we know that if we reduce the error or we reduce the residual, we're getting closer and closer to the right solution. Of course, we cannot pick just any arbitrary displacement function and just hope for the best. We have to think about the function in terms of the problem, of course, but there are also some mathematical limitations that we have to consider. For example, it has to satisfy all initial conditions of the problem, which is mostly important if we are dealing with dynamics problems. So it's not as relevant for this course, but I'm still mentioning it just to be complete. Next, it has to satisfy the boundary condition of the problem. Of course, if we choose a function that does not satisfy the boundary condition, we will never be able to reduce the error to 0 at these points. Finally, it also has to be a continuous function, since we have to be able to take the derivative of it to find the residual. Now, if all these categories are met, then it's a viable assumed approximate solution. Remember that in this case, as in all finite element problems, it holds that if you put garbage in, you will get garbage out. In this case, if you put in a wrong approximate displacement function, you will get a wrong displacement out of it, but still as close to possible as you can be. Now let's continue with this example, because it's much easier to study with an example, seeing what happens, rather than all the generic equations and discussions I've done so far. So let's just say that we take a polynomial function for u, since that's one of the easier assumed displacements which can be used in this case. So we can say that the assumed approximate solution now is a function of x, and for this example we go up to the third order polynomial to not give ourselves too much work in terms of calculations. So we have then c1 times x plus c2 times x squared plus c3 times x cubed, which satisfies all conditions. It is 0 at x is 0, and it's a continuous function. Now we have to determine c1, c2 and c3 so that I can get the exact solution to the problem, or at least minimize the residual. And please note that there's no constant term in this case because of the boundary condition. Because we know at x is 0, it has to be 0. Just to remind you, the residual is defined in this case as AE times the derivative of the approximate solution with respect to x minus p. Hence, I will start by taking the derivative of the approximate displacement, which gives me c1 plus 2 times c2 times x plus 3 times c3 times x squared. This way I find the residual to be the expression for A, the area, namely W1 plus W2 minus W1 over L times x times E times T times C1 plus 2 times C2x plus 3 times C3x squared minus P. Now, in the weighted formulation there are a number of different methods as already mentioned, but we're only going to look at the Galerkin method, and just as a reminder I'm showing the approximate function for u here as c1x plus c2x squared plus c3x cubed. In the Galerkin methods we have to use the so-called weighing functions, which have to be orthogonal to the residual. Now these weighing functions are denoted by wi, and in this case are equal to x, x squared and x cubed. The number of weighing functions will always be equal to the number of unknown coefficients that you want to determine, so you always get the same number of equations to solve as is the number of coefficients to determine. According to the definition of the Galerkin formulation, we enforce that the integral from a to b of the weighing function wi times the residual r is equal to 0. Hence we get n equations for n unknowns. If we continue with the example, we can substitute everything into the integral. So we know for our problem that the integral will be from 0 to L, because that's the length of our structure. Then we have the weighting function x times the residual, which we already calculated in one of the previous slides. Next we do the same with the second weighing function, so we have x squared times the residual. And finally also for the third weighing function, x cubed. So now we have these three equations in which everything is known except for the three constants c1, c2 and c3. In other words, this is a system we can solve. Now for this workout I will just give the final expression that you will find out if you work out the integral and solve the system. If you want to do these calculations yourself, this would be a good moment to pause the video. Working out the three expressions as a function of c1, c2 and c3 gives us the three equations that are shown here on the slide. Do note that I am not filling in any numbers yet, but keep using symbols so I can easily change the values later on. Finally, if we solve the system, we get the following expressions for c1, c2 and c3. These expressions may look difficult, but in the end all symbols just represent numbers, and I hope that by now you're not too scared by long expressions like these. Now ultimately we can combine these three constants and obtain the final expression for u as given at the bottom of this slide. As expected, it's a linear function of p, so if we double p we also double u, which is what we would expect. So it looks like it can be correct, but let's check that anyway. When plotting the analytical solution, here shown in the solid blue line, and also plotting the solution obtained with the Galerkin method using the green dots, we can see that our approximate solution was actually a good choice, because they're pretty much spot on. Of course, we could have made a different choice for approximate function, which would have given us a slightly different solution. The Galerkin method will always give you the values for the constant that will minimize the residual, but this does not mean you will always get a close match to the analytical solution. If you pick a wrong approximate displacement, then you will not get close to the analytical solution. For example, we could have taken a linear function in this case, and we would have not been as close as we are now. Now, I hope this overview was clear, but you may be wondering, when will we get to the final element formulation? You've only been talking about the analytical way so far, but this is a finite element course. So how does this help us to do that? Well, with the Galerkin method, it's actually very important that the weighing functions, which are also going to be used in the finite element formulation, are the same as the characteristics of the element, and that's called the shape function. Since we have not introduced you to the shape functions yet, that is what I'm going to do first in the next video, and afterwards I will return to setting up the finite element system with the Galerkin method. But now in the next video, first the shape functions. See you there.